Imagine something with me for a moment. Imagine two tiny particles of light, two photons, born together in a laboratory in Paris in the year 1982. They are created at the same instant, from the same atom, in the same flash of energy, and then they are sent flying apart in opposite directions at the speed of light. One photon races to the left, the other races to the right. They separate, they get farther and farther apart, a meter, 10 meters, 100 meters, a kilometer, 1,000 kilometers, 1,000,000 kilometers. Imagine one photon reaches New York, the other reaches Tokyo. They are now on opposite sides of the planet. They have no wire connecting them, no signal passing between them, no force, no field, no invisible thread linking them in any way that classical physics can describe. And now, a physicist in New York decides to measure a property of the photon that arrived there. She measures its polarization, the direction in which its electric field oscillates. And the instant she does, the instant she makes that measurement, something extraordinary happens. The photon in Tokyo, on the other side of the world, instantaneously, without any delay, without any signal traveling between them, assumes a correlated state. If the New York photon is measured as vertically polarized, the Tokyo photon is instantly horizontally polarized. Not in a second, not in a millisecond, not in a nanosecond. Instantly. As if the distance between them does not exist. As if space itself is an illusion. As if the two photons, despite being separated by the entire width of the planet, are somehow still one thing. One single, undivided entity, pretending to be two. This is not science fiction. This is not a thought experiment. This is not a metaphor. This was demonstrated conclusively in a laboratory in Orsay, France, in 1982, by a young physicist named Alain Aspect. And when his results came in, when the data was analyzed, when the numbers were checked and double-checked, when the conclusion was unavoidable, the physics establishment did something remarkable. They went quiet. They barely acknowledged it. They published the papers, filed them away, and went back to their work on particle accelerators and nuclear reactors and semiconductor devices, as if nothing had happened. As if reality had not just been shattered. As if the very foundations of everything we thought we knew about the universe had not just been pulled out from under our feet. And the question I want to explore with you today, the question that has haunted me ever since I first learned about this story, is this. Why? Why did the scientific establishment look away from one of the most profound experimental results in the history of human civilization? What did Alain Aspect actually prove? What were the implications that were so disturbing, so uncomfortable, so threatening, that an entire generation of physicists chose to pretend they did not exist? And what does this experiment tell us about the true nature of the reality you and I are sitting in right now? Today, we are going on a journey, and I want to be honest with you from the beginning. This is not going to be a quick summary. This is not going to be a surface-level overview. We are going deep. We are going to start at the very beginning, in a world where physics made sense, where the universe behaved itself, where cause and effect worked the way you would expect them to. And then we are going to watch that world crumble. We are going to meet the greatest minds of the 20th century. Albert Einstein, Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Max Planck, Richard Feynman. We are going to witness the greatest intellectual battle in the history of science, a battle between Einstein and Bohr that spanned decades and continents, a battle over nothing less than the nature of reality itself. We are going to meet John Bell, a quiet Irish physicist who worked at CERN, and who in his spare time, in his free moments between designing particle accelerators, she proved the most profound theorem in the history of physics. We are going to meet John Clauser, a young American experimentalist who risked his entire career to test that theorem in a laboratory in 1972, and who was rewarded for his groundbreaking discovery by being marginalized and sidelined for decades. And then we are going to arrive at 1982 at Alain Aspect's laboratory in France, at the moment when the question was finally, definitively, irrevocably answered. And then we are going to ask the question that nobody wanted to ask. What does it mean? What does it actually mean that the universe is not what we thought it was? What does it mean that two particles can be connected across infinite distances? What does it mean that the properties of things do not exist until you look at them? What does it mean that the universe, as the 2022 Nobel Prize Committee essentially confirmed, is not locally real? And we are not going to stop there. We are going to follow this story all the way through the decades of silence, through the loophole-closing experiments of the 21st century, through the delayed Nobel Prize that took 40 years to arrive, through the technological revolution that entanglement is now powering, quantum computers, quantum encryption, quantum teleportation, the quantum internet, technologies worth trillions of dollars, all built on the foundation of an experiment that the scientific establishment tried to bury. And we are going to confront the deepest implications, the ones that keep physicists awake at night, the ones that challenge everything we think we know about space, about time, about cause and effect, about the nature of existence itself. By the end of this journey, you will understand something that most people, including most physics students, are never taught properly. You will understand one of the deepest truths about the universe, and I promise you, once you understand it, you will never look at reality the same way again. So, if this sounds like a journey you want to take with me, I want you to do something right now. I want you to hit that subscribe button. I want you to click the bell icon so you never miss a video like this, and I want you to drop a comment right now telling me where you are watching from. What city? What country? I want to know, are you in Karachi? Are you in Delhi? Are you in London? Are you in New York? Are you in Lagos? Are you in Jakarta? Tell me. Let us see how far this video reaches. Let us see how many curious minds are out there, scattered across this planet, hungry to understand the deepest secrets of the universe. Tell me where you are, and let us begin. To understand what happened in 1982, to truly grasp why it matters, we need to start much earlier. We need to go back to a time when the universe made sense, when physics was comfortable, when reality was solid and predictable and behaved exactly the way you would expect it to. We need to go back to the world of Isaac Newton. In 1687, Isaac Newton published the Principia Mathematica, arguably the most important scientific work ever written. In it, Newton laid out the laws of motion and the law of universal gravitation, and in doing so, he gave humanity something extraordinary. He gave us a universe that was understandable, a universe that was predictable, a universe that operated like a vast, intricate, perfectly designed clockwork machine. In Newton's universe, if you knew the position and velocity of every single particle in existence at any given moment, you could, in principle, predict the entire future of the universe and retrodict its entire past. Every collision, every orbit, every falling apple, every rising tide, every flutter of a butterfly's wing, all of it determined by the inexorable mathematical laws that Newton had discovered. There was no randomness, there was no uncertainty, there was no mystery. There were just particles, forces, and mathematics. And the math worked. It worked with breathtaking precision. It predicted the orbits of the planets. It predicted the trajectories of cannonballs. It predicted the behavior of tides and pendulums and springs and gears. The universe was a machine, and Newton had found the instruction manual. This idea, the idea of a deterministic clockwork universe, was captured beautifully by the French mathematician Pierre-Simon Laplace in the early 1800s. Laplace imagined a hypothetical superintelligent being, later called Laplace's demon, that knew the position and momentum of every single particle in the universe at a single instant in time. Such a being, Laplace argued, could use Newton's laws to calculate the entire future and the entire past of every particle, every object, every person, every star, every galaxy. The future would be completely determined. The past would be completely determined. Free will would be an illusion. Surprise would be an illusion. Mystery would be an illusion. Everything that ever happened and everything that ever will happen would be a necessary, inevitable consequence of the initial conditions of the universe and the laws of physics. Now, whether or not Laplace's demon is truly possible is a deep philosophical question. But the point is that in Newton's universe the idea made sense. The mathematics supported it. Every experiment confirmed it. And more importantly, this universe rested on two fundamental assumptions, two pillars that seemed so obviously true, so self-evidently correct, that nobody even thought to question them. The first pillar was locality. Locality means that an object can only be directly influenced by its immediate surroundings. If I want to push a ball, I have to touch it, or touch something that touches it. Influences travel through space. They have a speed limit. After Einstein's special theory of relativity in 1905, we knew what that speed limit was. The speed of light, 299,792,458 meters per second. Nothing, no influence, no signal, no information, nothing at all, can travel faster than light. If a star explodes 10 light-years away, we will not feel its effects for 10 years. That is locality. Things that are far apart cannot influence each other instantly. There must always be a signal, a messenger, something that carries the influence from one place to another, and that messenger is limited by the speed of light. The second pillar was realism. Realism means that objects have definite properties whether or not anyone is looking at them. The moon is there whether or not you look at it. A ball is red whether or not anyone sees it. An electron has a definite position whether or not you measure it. Properties are real. They exist objectively, independently of observation. The universe is out there, doing its thing, regardless of whether conscious beings are watching. These two pillars, locality and realism, are not just physics concepts. They are the foundations of common sense. They are the basis of everything you have ever experienced. You have never seen an object in two places at once. You have never seen an influence travel faster than light. You have never seen the moon disappear when you closed your eyes. Locality and realism are not just how physics works, they are how reality works, or so we thought. By the late 1800s, physics was feeling confident. Very confident. Perhaps overconfident. The Scottish physicist Lord Kelvin reportedly said something to the effect that physics was essentially complete, with just two small clouds on the horizon, two small puzzles remaining to be solved. Everything else was understood. The clockwork universe was ticking along beautifully. Those two small clouds would turn out to be the seeds of the two greatest scientific revolutions in history. One cloud led to Einstein's theory of relativity, which shattered our understanding of space, time, and gravity. The other cloud led to quantum mechanics, which shattered everything else, and it is quantum mechanics that concerns us today. Because quantum mechanics did not merely tweak the clockwork universe. It did not make minor adjustments to Newton's machine. It took a sledgehammer to the machine. It smashed it into pieces. And then, from the wreckage, it built something so strange, so alien, so fundamentally incomprehensible to the human mind that even the physicists who created it could not agree on what it meant. They still cannot agree. 100 years later, the smartest people on the planet still argue about what quantum mechanics is telling us about reality. And the story of that argument, the story of that disagreement, the story of the experiment that should have settled it, and the decades of silence that followed, that is what we are here to explore. The quantum revolution began in the year 1900 in Berlin with a physicist named Max Planck, and it began almost by accident. Planck was trying to solve a very specific, very technical problem. The problem was about how hot objects emit light. When you heat up a piece of metal, it glows. First red, then orange, then yellow, then white. Classical physics, the physics of Newton and Maxwell, could describe this process, but only up to a point. When physicists tried to calculate the amount of energy emitted at very short wavelengths, at ultraviolet frequencies and beyond, the equations went haywire. They predicted that a hot object should emit infinite energy at ultraviolet frequencies. This was obviously wrong. Hot objects do not emit infinite energy. If they did, every oven, every fireplace, every candle would destroy the universe. This embarrassing failure of classical physics was called the ultraviolet catastrophe, and it was one of Lord Kelvin's two small clouds. Max Planck, in a moment of mathematical desperation, found a way to fix the equations. But his fix required a bizarre assumption. He had to assume that energy is not continuous. Energy does not flow smoothly like water from a tap. Instead, energy comes in tiny, discrete packets, which Planck called quanta, from the Latin word for how much. Each quantum of energy has a size proportional to the frequency of the light. High-frequency light, like ultraviolet, comes in bigger quanta. Low-frequency light, like radio waves, comes in smaller quanta. This seemingly innocuous mathematical trick fixed the ultraviolet catastrophe perfectly. The equations now gave the right answers. But Planck himself did not really believe that energy actually comes in packets. He thought it was just a mathematical convenience, a computational trick, not a description of how nature actually works. He was wrong. He had just discovered one of the most fundamental properties of the universe. Energy is quantized. Reality comes in chunks, and there is no going back. 5 years later, in 1905, a young clerk in the Swiss patent office named Albert Einstein took Planck's idea and ran with it. Einstein was working on the photoelectric effect, a puzzling phenomenon in which light shining on a metal surface ejects electrons from the surface. The puzzle was that the energy of the ejected electrons depended on the color of the light, not on its brightness. Red light, no matter how bright, could not eject electrons from certain metals, but even dim blue light could. Classical physics could not explain this. Light was supposed to be a wave, and the energy of a wave depends on its amplitude, its brightness, not its frequency. But Einstein, in using Planck's idea of energy quanta, proposed a radical explanation. Light is not just a wave. Light is also a particle. Each particle of light, which Einstein called a photon, carries a fixed amount of energy proportional to its frequency. Blue photons carry more energy than red photons. When a blue photon hits an electron, it transfers enough energy to kick the electron out of the metal. When a red photon hits an electron, it does not have enough energy, no matter how many red photons you send. The photoelectric effect is explained, but at a cost. Light is now both a wave and a particle, both at the same time. This is what we call wave-particle duality, and it makes absolutely no intuitive sense. How can something be both a wave, spread out across space, and a particle, concentrated at a point? This question would haunt physics for decades, and it is still, in a very deep sense, unanswered. Now, here is something ironic, something deeply, beautifully ironic. Albert Einstein, the man who would spend the second half of his life fighting against quantum mechanics, trying to destroy it, trying to prove it wrong, was one of the people who helped create it. His 1905 paper on the photoelectric effect was one of the foundational stones of quantum theory. In fact, it was this paper, not the theory of relativity, for which Einstein won the Nobel Prize in physics in 1921. The father of relativity won his Nobel Prize for quantum mechanics. The universe has a sense of humor. Over the next 2 decades, quantum mechanics developed rapidly. In 1913, Niels Bohr, though a Danish physicist working in Manchester and Copenhagen, proposed a new model of the atom. In Bohr's model, electrons orbit the nucleus of an atom not in any orbit they please, as classical physics would allow, but only in certain specific quantized orbits. They can jump from one orbit to another, absorbing or emitting a photon when they do, but they cannot exist between the orbits. This explained the discrete spectral lines that elements produce when heated, and it was a triumph for the quantum idea. But it was also deeply strange. Why should orbits be quantized? What prevents the electron from being in between? These questions had no satisfactory answers. The quantum world was beginning to reveal its alien nature. Then, in the mid-1920s, the quantum revolution exploded. In 1925, a young German physicist named Werner Heisenberg, just 23 years old, developed a mathematical framework for quantum mechanics called matrix mechanics. It was abstract, unfamiliar, and difficult to visualize, but it worked. It predicted experimental results with stunning accuracy. Almost simultaneously, in 1926, the Austrian physicist Erwin Schrödinger developed a different mathematical framework called wave mechanics. Schrödinger's approach was based on a wave equation, an equation that describes how a wave function, denoted by the Greek letter psi, evolves over time. This wave function contains all the information about a quantum system. Everything you can possibly know about a particle is encoded in its wave function. And the beauty of Schrödinger's equation is that it tells you how the wave function changes from moment to moment, how it flows and oscillates and interferes with itself, how it spreads out through space like a ripple on a pond. But here is where things get deeply, profoundly weird. What is the wave function? What does psi actually represent? Schrödinger initially believed it represented a real, physical wave, like an ocean wave or a sound wave. The electron is literally smeared out in space, spread across a region, existing in many places at once. But Max Born, a German physicist, proposed a different interpretation. He said the wave function is not a real physical wave. It is a probability wave. The square of the wave function at any point in space gives you the probability of finding the particle at that point when you measure it. The particle is not literally everywhere at once. Rather, there is a probability of finding it at many different places, and the wave function tells you what those probabilities are. Born's interpretation was accepted by most physicists, and it became part of the standard framework of the quantum mechanics. But it introduced something truly disturbing. If the wave function only gives probabilities, then before you measure a particle, you cannot say where it is. It does not have a definite position. It is not that we do not know its position. It is that the position does not exist until we measure it. Before measurement, the particle exists in a superposition of all possible positions, a ghostly cloud of potentiality. Not here, not there, but somehow everywhere at once, with different probabilities for different places. And then, when you measure it, the wave function collapses. All the potentiality vanishes. The ghostly cloud snaps into a single point. The particle appears at one specific location, and the probability of finding it anywhere else drops instantly to zero. This is the measurement problem. And it is, in my view, the deepest and most disturbing problem in all of physics. Before measurement, the particle has no definite position. It exists in superposition. After measurement, it has a definite position. The wave function has collapsed. But what is a measurement? What triggers the collapse? Why should the act of measuring be special? Who or what counts as an observer? Does the observer have to be conscious? Does a camera count? Does a rock count? These questions have no agreed-upon answers. A century of debate, and we still do not know what happens when a quantum measurement occurs. We do not know why measurement is special. We do not know whether collapse is real or an illusion. We do not know what the wave function actually is. And this is not because we have not thought hard enough about it. It is because the problem is genuinely, ferociously difficult. It may be the hardest problem in science. In 1927, Werner Heisenberg proved one of the most famous results in quantum mechanics: the uncertainty principle. Heisenberg showed that there is a fundamental limit to how precisely you can simultaneously know certain pairs of properties of a particle. The most famous pair is position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a limitation of our instruments. It is not that our measuring devices are too crude. It is a fundamental property of nature. The universe itself does not have a definite value for both position and momentum at the same time. It is as if reality is blurry at the quantum level, not because our vision is poor, but because reality genuinely is blurry. Let me pause here and talk about the experiment that Richard Feynman, one of the greatest physicists of the 20th century, called the heart of quantum mechanics: the double-slit experiment. If you understand the double-slit experiment, you understand, in Feynman's words, the only mystery in quantum mechanics. Everything else is just variations on this theme. Here's the setup. You have a source that fires particles, let us say electrons, one at a time, toward a barrier. The barrier has two narrow slits in it. Behind the barrier is a detection screen that records where each electron hits. Now, if electrons were tiny bullets, like little balls of matter, you would expect a simple result. Some electrons would go through the left slit and pile up behind it. Other electrons would go through the right slit and pile up behind that one. You would see two bands of hits on the screen, one behind each slit. This is exactly what you see if you fire actual bullets through two slits. Common sense, straightforward, but that is not what happens with electrons. When you fire electrons one at a time through the double slit and let them accumulate on the screen, you do not see two bands. You see an interference pattern, an alternating series of bright and dark bands, exactly like what you would see if you sent a wave through two slits. When a wave passes through two slits, the waves from each slit overlap and interfere with each other. Where the peaks of one wave align with the peaks of the other, you get constructive interference, a bright band. Where the peak of one aligns with the trough of the other, you get destructive interference, a dark band. The interference pattern is a signature of wave behavior. And the electrons, these tiny particles of matter, produce an interference pattern. They behave like waves. But here is what makes it genuinely terrifying. You are firing the electrons one at a time. There is only one electron in the apparatus at any given moment. So what is it interfering with? How can a single electron produce an interference pattern? The electron would have to pass through both slits simultaneously, interfere with itself, and then arrive at a single point on the screen. One particle going through two slits at the same time. This makes no classical sense, and yet it is what the experiment shows. Every single time. Now hold on, it gets worse, much worse. Suppose you decide to figure out which slit the electron actually goes through. You place a detector at one of the slits, a tiny device that records whether an electron passes through it. Now you fire the electrons one at a time, and you watch. And the moment you do this, the moment you have information about which slit the electron went through, the interference pattern disappears. The electrons now behave like particles, not waves. You see two bands, not an interference pattern. The act of observation, the act of gaining which path information, destroys the wave behavior. If you look, the electron goes through one slit. If you do not look, it goes through both, as if the electron knows whether it is being watched. I want to make this absolutely clear. This is not some obscure theoretical prediction. This is not a mathematical abstraction. This is what actually happens in laboratories around the world. This experiment has been performed millions of times with electrons, with photons, with neutrons, with atoms, even with large molecules consisting of hundreds of atoms. The result is always the same. If you do not observe which path the particle takes, it behaves like a wave, going through both slits and producing interference. If you do observe which path it takes, it behaves like a particle, going through one slit and producing no interference. The act of measurement changes the behavior. Reality depends on whether you are looking. Feynman said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." He also said that the double-slit experiment contains the only mystery. I think he was right. Everything strange about quantum mechanics, superposition, entanglement, the measurement problem, the collapse of the wave function, all of it is contained in the double-slit experiment. If you truly understand what this experiment is telling us, you understand the deep mystery at the heart of reality. And if you think it makes sense, you are not paying attention. Now, by the late 1920s, quantum mechanics had a complete mathematical framework and an interpretation. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg. The Copenhagen interpretation says roughly the following. Before measurement, a quantum system exists in a superposition of all possible states. The wave function describes all these possibilities and their probabilities. When a measurement is made, the wave function collapses to one definite state. You cannot predict which state it will collapse to, only the probability of each possible outcome. And here is the crucial part. You should not ask what the system was doing before you measured it. Before measurement, the system does not have a definite state. It is not that you do not know its state. It is that the state does not exist. Reality at the quantum level is not determined until it is observed. Bohr took this even further. He argued that it is meaningless to talk about the properties of a quantum system independently of the measurement context. The measurement apparatus and the quantum system are inseparable. You cannot describe the electron independently of the experiment you use to observe it. There is no objective, observer-independent reality at the quantum level. Quantum mechanics is not a description of reality. It is a description of what we can observe. And asking what is really happening when we are not looking is not just unanswerable. It is a meaningless question. This was, and remains, a deeply unsatisfying position for many physicists. It was certainly unsatisfying for Albert Einstein, and this dissatisfaction, this refusal to accept that reality dissolves when you are not looking, would lead to the greatest intellectual battle in the history of science. The first rounds of this battle were fought at the Solvay conferences, a series of elite gatherings of the world's top physicists, held in Brussels, Belgium. The 1927 Solvay Conference was particularly legendary. The photograph taken at that conference is one of the most famous images in the history of science. 29 of the greatest physicists in history, including Einstein, Bohr, Heisenberg, Schrödinger, Planck, Dirac, Born, de Broglie, Pauli, and Lorentz, all gathered in one room. 17 of the 29 were or would become Nobel Prize winners. And at this conference, Einstein and Bohr began their epic debate. Einstein did not believe that quantum mechanics was the final word on reality. He did not believe that the universe was fundamentally random. He did not believe that particles could be in two places at once. He did not believe that reality depended on observation. He believed that quantum mechanics was an incomplete theory, a statistical description that captured some true features of reality but was missing something. There had to be a deeper level of description, a more complete theory, one that restored determinism, locality, and realism. There had to be hidden variables, additional information that quantum mechanics did not capture, but that determined the outcomes of measurements in advance. The randomness of quantum mechanics was not fundamental. It was merely a reflection of our ignorance, like the randomness of a coin toss. A coin toss is not truly random. If you knew the exact initial conditions, the force, the angle, the air resistance, you could predict which side would land up. The coin has a definite trajectory. The randomness is in your lack of knowledge, not in the physics. Einstein believed quantum mechanics was the same. The electron has a definite trajectory. The randomness is in our ignorance of the hidden variables, not in the physics. Einstein's strategy at the Solvay conferences was brilliant. He would come to breakfast each morning with a thought experiment, an ingenious scenario designed to show that quantum mechanics leads to a contradiction or an absurdity. He would present it to Bohr, and then Bohr would spend the rest of the day and often the night finding the flaw in Einstein's argument. And Bohr always found one. Every time. Each of Einstein's thought experiments, no matter how clever, was refuted by Bohr, using the principles of quantum mechanics itself. By the end of the 1930 Solvay conference, Einstein's attacks had all been repelled. Bohr's defenders had held the line. But Einstein was not done. He was saving his most powerful weapon. That weapon came in 1935 in a paper that would become one of the most cited and most debated papers in the history of physics. It was written by Einstein along with two younger physicists, Boris Podolsky and Nathan Rosen, and it is known as the EPR paper, after the initials of its authors. The paper was titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And its answer was no. The EPR argument is one of the most elegant and devastating arguments in the history of science. Let me explain it carefully, because everything that follows in this story depends on understanding what Einstein, Podolsky, and Rosen were saying. Imagine you create two particles that interact with each other and then fly apart. Because of how they were created, quantum mechanics tells us that certain properties of the two particles are correlated. For example, if the total momentum of the system is zero, then the two particles must have equal and opposite momenta. If particle A has momentum p, particle B has momentum negative p. Similarly, if the two particles are created at the same point, the positions of the two particles are correlated. The sum of their positions is always twice the position of the point where they were created. Now here is the key insight. According to quantum mechanics, if you have not measured a particle's position, it does not have a definite position. And if you have not measured its momentum, it does not have a definite momentum. Furthermore, the uncertainty principle says you cannot simultaneously know both the position and momentum of a single particle with arbitrary precision. So, you have to choose. Measure position or measure momentum. You cannot measure both. But now, Einstein said, consider this. The two particles have flown apart. They are now far away from each other. You choose to measure the position of particle A. You get a definite result, say particle A is at position X. Because of the correlation, you now know that particle B is at a corresponding position. You did not measure particle B. You did not touch it. You did not interact with it in any way, but now you know its position. Alternatively, you could have chosen to measure the momentum of particle A instead. You would get a definite result, say momentum P. Because of the correlation, you now know that particle B has momentum negative P, again, without touching particle B. Now, Einstein argued, particle B is far away. Your measurement of particle A cannot have instantaneously affected particle B, because nothing can travel faster than light. Whatever particle B is doing, it was doing it before you measured particle A. Your choice of what to measure on particle A cannot change the physical state of particle B. This is locality. Influences cannot travel faster than light. But notice what you can do. By choosing to measure the position of particle A, you can determine the position of particle B without disturbing it. Alternatively, by choosing to measure the momentum of particle A, you can determine the momentum of particle B without disturbing it. In both cases, you learn something about particle B without touching it. Since your measurement of particle A cannot affect particle B, whatever property of particle B you can determine must have existed before you made the measurement. If you can determine particle B's position by measuring particle A, then particle B must have had a definite position all along. And if you can determine particle B's momentum by measuring particle A, then particle B must have had a definite momentum all along. But quantum mechanics says particle B cannot have both a definite position and a definite momentum simultaneously. That is the uncertainty principle. Therefore, Einstein concluded, quantum mechanics must be incomplete. There must be hidden variables, additional information not captured by the quantum description, that determine both the position and momentum of particle B in advance. Quantum mechanics, with its uncertainty and its superposition and its measurement-dependent reality, is not the full story. It is missing something. This was Einstein's masterpiece. It was elegant, it was logical, it was devastating, and it rested on one key assumption: locality. The assumption that measuring particle A cannot instantaneously affect particle B when they are far apart. Einstein called this instantaneous correlation between distant particles "Spukhafte Fernwirkung" in German. Spooky action at a distance. He meant it as a term of ridicule, a way of highlighting the absurdity of quantum mechanics. If quantum mechanics were right, and particles truly did not have definite properties until measured, then measuring one particle would somehow instantaneously determine the state of the other, no matter how far apart they were. And that, Einstein argued, was spooky. That was absurd. That could not be how the universe works. Now, I want to highlight something about this moment, because it is one of the most misunderstood episodes in the history of physics. Einstein was not attacking quantum mechanics because he did not understand it. He was not some crank who could not follow the math. He was not stuck in an old-fashioned way of thinking. Einstein understood quantum mechanics perfectly. He helped create it. He understood the mathematics. He understood the predictions. He understood the experimental evidence, and that is precisely why he was so troubled. He understood exactly what quantum mechanics was saying, and he was horrified by it. His attack was not born of ignorance. It was born of the deepest possible understanding, combined with a profound philosophical conviction that the universe must be local and real. Niels Bohr's response to the EPR paper was complicated, and many physicists have argued not entirely satisfying. Bohr essentially argued that Einstein was making an unjustified assumption about the separability of distant particles. In quantum mechanics, Bohr said, once two particles have interacted, they cannot be treated as independent entities, even after they are separated. Measuring particle A does not merely reveal pre-existing information about particle B. The measurement of particle A is an integral part of the context in which particle B's properties are defined. You cannot separate the properties of particle B from the measurement performed on particle A. This is not because some signal travels between them, but because the two particles form an indivisible whole, a single quantum system, regardless of how far apart they are. Now, at the time, it was not clear who was right. Both arguments had logical force. Einstein's argument rested on locality, the principle that distant objects cannot influence each other instantaneously, which seemed obviously true and was supported by special relativity. Bohr's argument rested on the quantum principle that entangled particles cannot be described independently, which was mathematically correct within the framework of quantum mechanics but philosophically challenging. The debate seemed unresolvable, a philosophical stalemate, and for almost 3 decades, that is exactly what it was. But before we move on, I want to mention something that happened in the immediate aftermath of the EPR paper, because it is one of the most important moments in the history of physics, and it involves the coining of a word that would come to define an entire field of science. Erwin Schrödinger, the Austrian physicist who had developed the wave equation that bears his name, read the EPR paper and was deeply affected by it. Schrödinger was one of the few physicists of his generation who took the EPR argument seriously. He was troubled by the implications of quantum mechanics, and in response to the EPR paper, he wrote his own paper in 1935, in which he analyzed the phenomenon of correlated particles in detail. In this paper, Schrödinger needed a word for the strange connection between particles that Einstein had described. He chose a German word, Verschränkung. In English, this was translated as entanglement, and Schrödinger said something remarkable about it. He called entanglement not one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Not a characteristic trait, the characteristic trait, the single most important, most distinctive, most revolutionary feature of quantum mechanics, the thing that makes it fundamentally different from all classical physics that came before it. Schrödinger was right. Entanglement is not just one weird feature of quantum mechanics among many. It is the feature. It is the beating heart of the quantum world. It is what makes quantum mechanics fundamentally, irrevocably different from any classical theory. And its implications, as we will see, are staggering. And this is also the paper in which Schrödinger proposed his famous cat thought experiment. You have probably heard of Schrödinger's cat, even if you have never studied physics. Here's what it actually says. Imagine a cat in a sealed box. Inside the box there is also a tiny amount of a radioactive substance, a Geiger counter, and a vial of poison. If the radioactive substance decays, the Geiger counter detects the decay and triggers a mechanism that breaks the vial and kills the cat. If the radioactive substance does not decay, the cat remains alive. Now, according to quantum mechanics, the radioactive substance is in a superposition of decayed and not decayed until it is measured. And, since the cat's fate is directly tied to the radioactive substance, the cat, according to quantum mechanics, is also in a superposition of dead and alive. The cat is simultaneously dead and alive until someone opens the box and observes it. Upon observation, the wave function collapses, and the cat is found to be either dead or alive. Now, here's the critical point that is often missed. Schrödinger did not propose this thought experiment because he agreed with quantum mechanics. He proposed it because he thought it was absurd. He was using the cat to highlight the ridiculousness of the Copenhagen interpretation. He was saying, look, if you take quantum mechanics seriously, if you really believe that things do not have definite properties until they are observed, then you have to accept that a cat can be simultaneously dead and alive. And that is obviously insane. Therefore, quantum mechanics must be missing something. But here is the irony. Instead of destroying quantum mechanics, Schrödinger's cat became the most famous illustration of it. Instead of exposing the absurdity, it became an icon of quantum weirdness. The thought experiment that was supposed to be a reductio ad absurdum, a demonstration that something must be wrong, became a celebrated feature of the theory. The universe, once again, has a sense of humor. After the EPR paper and Schrödinger's response, the debate between Einstein and Bohr entered a kind of stalemate. Most physicists sided with Bohr. Not necessarily because they found Bohr's arguments more convincing, but because quantum mechanics worked. It predicted experimental results with extraordinary accuracy. It explained the behavior of atoms, of molecules, solids, light, and chemical bonds. It was the foundation of nuclear physics, semiconductor physics, and quantum electrodynamics. And if you wanted a career in physics, you used quantum mechanics to solve problems. You did not spend your time worrying about what it meant. This pragmatic attitude hardened in the 1940s and 50s. The culture of physics shifted. The focus moved to calculation, to prediction, to building things. Nuclear weapons, nuclear power, transistors, lasers, semiconductors. The Cold War demanded applied physics, and applied physics demanded that you use quantum mechanics, not question it. A slogan emerged that captured this attitude perfectly. It is usually attributed to David Mermin, paraphrasing Richard Feynman, and it goes like this: shut up and calculate. Do not ask what quantum mechanics means. Do not ask what the wave function represents. Do not ask what happens during a measurement. Just use the equations. They work. That is all that matters. And so the question that Einstein had raised, the question of whether quantum mechanics was complete, the question of whether there were hidden variables, the question of whether the universe was truly non-local and non-real, that question was shelved, not answered, not refuted, just shelved, put in a drawer, forgotten, ignored for 29 years. And then, in 1964, a quiet Irish physicist named John Stuart Bell pulled it out of the drawer and changed everything. John Bell was born in Belfast, Northern Ireland, in 1928. He came from a working-class family and was the first in his family to attend university. He studied physics at Queen's University, Belfast, and then at the University of Birmingham. He went to work at CERN, the European Organization for Nuclear Research, in Geneva, Switzerland, where he designed particle accelerators. This was his day job, his bread and butter, the work that paid the bills and sustained his career. But Bell had a secret passion, a passion that he knew, in the culture of physics at the time, could damage his reputation if he pursued it too openly. He was passionate about the foundations of quantum mechanics. He was troubled by the Copenhagen interpretation. He thought the questions Einstein had raised were real questions, important questions, questions that deserved answers, not dismissal. Bell had a particular grievance with a famous theorem by the Hungarian-American mathematician John von Neumann. In 1932, von Neumann had published what was widely believed to be a proof that hidden variable theories were impossible. A proof that no theory with hidden variables could reproduce the predictions of quantum mechanics. This proof was accepted by most physicists and was used as a justification for not pursuing hidden variable theories. If von Neumann had proven them impossible, why bother? But Bell, through careful analysis, found a flaw in von Neumann's proof. Von Neumann had made an assumption that was too strong, an assumption that was not physically necessary. His proof did not actually rule out all hidden variable theories. It only ruled out a very specific class of them. This was an important realization, but it was only the beginning of Bell's journey. In 1964, Bell asked a question that no one else had thought to ask, or rather, a question that no one else had been brave enough to ask. He asked, "Can we experimentally distinguish between quantum mechanics and local hidden variable theories? Is there an experiment, a real, physical, doable experiment, that would give different results depending on whether quantum mechanics was right or Einstein was right?" And he found the answer. Yes. Bell derived a mathematical inequality, now known as Bell's inequality, that must be satisfied by any theory that is both local and realistic. Any theory in which particles have definite properties, realism, and in which influences cannot travel faster than light, locality, must predict correlations between measurements on distant particles that satisfy a certain mathematical bound. The correlations cannot be too strong. There is a ceiling, a maximum value, that the correlations can reach in any local hidden variable theory. But quantum mechanics predicts correlations that exceed this bound. Quantum mechanics predicts that the correlations between measurements on entangled particles are stronger than any local realistic theory can produce. Let me try to make this concrete. Imagine you and a friend are playing a game. You are in separate rooms. You cannot communicate. A referee sends each of you a question, randomly chosen. You each answer your question independently. Now, there are correlations between your answers because before the game started, you and your friend agreed on a strategy. You decided in advance what answers to give for each possible question. This is a local realistic strategy. You each have your answers predetermined, realism, and you cannot communicate during the game, locality. Now, it turns out that for certain games there is a mathematical limit to how well correlated your answers can be using any local realistic strategy. No matter how clever your prearranged strategy, you cannot exceed a certain score. This limit is Bell's inequality, but quantum mechanics allows you to exceed the limit. If, instead of prearranged answers, you and your friend share a pair of entangled particles and use quantum measurements to determine your answers, you can achieve stronger correlations than any classical strategy allows. You can beat the Bell inequality. Now, the specific version of Bell's inequality that became most important for experiments is called the CHSH inequality, named after John Clauser, Michael Horn, Abner Shimony, and Richard Holt, who derived it in 1969. The CHSH inequality puts a specific numerical bound on the correlations. For any local hidden variable theory, a certain combination of correlation measurements denoted S must satisfy S less than or equal to 2. That is the ceiling, that is the classical limit. But quantum mechanics predicts that for entangled particles, S can be as high as 2 times the square root of 2, which is approximately 2.828. This is the Cyrilson bound, the maximum quantum mechanical prediction. So, the test is simple. Create pairs of entangled particles. Measure them. Calculate S. If S is less than or equal to 2, Einstein was right. Local hidden variables exist. Quantum mechanics is incomplete. If S exceeds 2, quantum mechanics is right. Local hidden variables are ruled out. The universe is not what Einstein thought it was. Either locality or realism or both must be abandoned. Bell had turned a philosophical debate into a physics experiment. He had taken a question that Einstein and Bohr argued about over breakfast and turned it into a question that could be answered in a laboratory. This was, in my view, one of the single greatest intellectual achievements of the 20th century. Bell did not just contribute to physics. He transformed the very nature of the question. He showed that the deepest questions about reality are not merely philosophical, they are empirical, they can be tested. Nature itself can tell us the answer. But here is where the story takes a dark turn. Bell published his inequality in 1964 in a journal called Physics Physique Physica. This was a relatively obscure journal. It was not one of the prestigious, high-profile journals that every physicist reads. It was a small journal that would, in fact, be discontinued just a few years later. And the physics community, by and large, ignored Bell's paper. Almost nobody noticed. Almost nobody cared. The paper that contained the most profound theorem in the history of physics was published in a journal that almost nobody read. And even those who did read it, for the most part, shrugged and moved on. Why? Because of the culture of shut up and calculate. Because questioning the foundations of quantum mechanics was not considered legitimate physics. Because the Cold War physics machine was focused on practical applications, not philosophical puzzles. Because John Bell was a CERN accelerator designer, not a big-name professor at Harvard or Princeton. Because the question of hidden variables was considered settled by von Neumann's flawed proof. Because the physics establishment had decided that certain questions were not worth asking. I want you to sit with that for a moment. The most important theorem in the history of physics. A theorem that could experimentally resolve the greatest debate in science. A theorem that would eventually earn a Nobel Prize. Published in an obscure journal. Ignored by the establishment. For years. And this is the moment when I want to take a breath and ask you something. If you are watching this and you are finding yourself drawn in, if you are feeling the weight of this story, if you are beginning to see why this matters, I want you to do something for me. I want you to hit that like button, not for me, for the algorithm. The algorithm decides who sees this video, and the only way videos like this, long-form, deep-dive, serious science content, the only way they reach more people is if you engage. So hit that like button and tell me in the comments, did you know about Bell's theorem before this video? Had you heard of it? Let me know, because I want to understand where you are starting from. Now, let us move forward. Bell's inequality existed. It was a theoretical result, a mathematical inequality on paper. To actually test it, someone had to build an experiment. Someone had to create entangled particles, measure them, and calculate S. Someone had to put their career on the line and do the experiment that the physics establishment did not want done. That someone was John Clauser. John Clauser was an American physicist, born in 1942. He studied at the California Institute of Technology and then at Columbia University, where he earned his Ph.D. As a graduate student, Clauser read Bell's paper and immediately grasped its significance. He understood what Bell had done. He understood that this was testable. And he became obsessed with testing it. But when Clauser began telling people about his plans, the reaction was not encouraging. He approached Richard Feynman, one of the most famous physicists in the world, and told him about the idea of testing Bell's inequality. Feynman dismissed him. He essentially told Clauser that the experiment was a waste of time. Quantum mechanics was obviously right. Why bother testing something everyone already knew? Clauser's thesis advisor warned him that pursuing this line of research could damage his career. The message from the physics establishment was clear. Do not do this. It is not worth doing. It will not help you get a faculty position. It will not get you grants. It will get you labeled as a crackpot who wastes time on philosophy instead of doing real physics. John Clauser did it anyway. In 1972, together with Stuart Friedman, a graduate student at the University of California, Berkeley, Clauser performed the first experimental test of Bell's inequality. They used calcium atoms that, when excited, produced pairs of entangled photons through a process called atomic cascade. The two photons flew off in opposite directions. Clauser and Friedman measured the polarization of each photon using polarizing filters set at various angles. They collected data. They calculated S. The result was clear. Bell's inequality was violated. The correlations between the entangled photons were stronger than any local hidden variable theory could produce. S exceeded 2. Quantum mechanics was right. Einstein's vision of a local, realistic universe, a universe where particles have definite properties and where influences cannot travel faster than light, was wrong. This was, in principle, one of the most important experimental results in the history of science. This was the first direct evidence that the universe is not locally real. This should have been front-page news. This should have triggered a revolution. This should have changed the direction of physics. It did not. The physics community largely ignored the result. The papers were published. Some specialists in quantum optics noticed. A handful of people appreciated the significance. But the broader physics community, the people running departments, the people awarding grants, the people writing textbooks, they moved on. Bell's inequality was violated. So what? Quantum mechanics works. We already knew that. What else is new? And Clauser paid a price. Despite having performed a groundbreaking experiment, he struggled to find an academic position. He was told, in so many words, "Nice experiment, but maybe stop wasting your time on this." The man who had performed the first experimental test of the most profound theorem in physics was sidelined, marginalized. His career suffered because he had dared to ask a question that the establishment considered unimportant. I want to emphasize this because it is a crucial part of the story. The burial of quantum entanglement's implications was not a conspiracy. There was no secret meeting of physicists who decided to suppress the truth. It was something more subtle and in some ways more insidious. It was a cultural consensus, an unspoken agreement that certain questions were not legitimate, that certain experiments were not important, that certain ideas were not worth pursuing. It was the shut up and calculate mentality, weaponized against anyone who dared to think too deeply about what the calculations meant. And this cultural consensus had real consequences. It delayed the development of quantum information science by decades. It cost brilliant researchers their careers, and it meant that one of the most important discoveries in the history of physics was treated as a curiosity, a footnote, a philosophical amusement, rather than the earth-shattering revelation it truly was. But the story was not over, because while the establishment ignored Clauser's result, a young French physicist was paying very close attention. Alain Aspect was born in 1947 in Agen, a small town in southwestern France. He studied physics at the École Normale Supérieure de Cachan and at the Université Paris-Sud. In the mid-1970s, while working on his doctoral thesis, Aspect read Bell's papers and, like Clauser before him, was electrified. He saw what Bell had done. He understood the importance, and he also saw something else. He saw that Clauser's experiment, while groundbreaking, had loopholes. Potential weaknesses that, in principle, could allow a local hidden variable theory to explain the results without invoking quantum non-locality. There were two main loopholes. The first was the locality loophole. In Clauser's experiment, the polarizer settings were fixed throughout the experiment. They were set before the measurement began and not changed during the flight of the photons. This meant that, in principle, a hidden variable theory could exploit this. If the polarizer settings were fixed, then some kind of signal could, in theory, travel from one detector to the other and inform the particles what to do. Even though such a signal would have to travel faster than light if the detectors were close together, the fact that the settings were fixed meant you could not completely rule out local explanations. The second was the detection loophole. Not all photons produced in the experiment were actually detected. Most of them were lost along the way. This meant you had to assume that the detected photons were a representative sample of all the photons produced. This is called the fair sampling assumption. But in principle, a clever hidden variable theory could exploit this. Maybe the photons that were detected were a biased sample, and if you could detect all of them, the correlations would actually satisfy Bell's inequality. Aspect decided to close the locality loophole. He would design an experiment where the polarizer settings were changed during the photon's flight, so fast that no signal, even one traveling at the speed of light, could travel from one detector to the other in time to influence the measurement. This would slam the door on the locality loophole. Before beginning his experiments, Aspect did something brave. He traveled to CERN to meet John Bell personally. He wanted to discuss his plans with the man who had made it all possible. And Bell's reaction was telling. Bell was excited. He thought the experiment was important and needed to be done, but he asked Aspect a question that revealed everything about the culture of physics at the time. He asked, "Do you have tenure?" Think about that for a moment. The man who had proven the most profound theorem in physics was asking a young experimenter before he embarked on the experiment whether his career was safe. Because Bell knew. He knew what would happen if Aspect pursued this. He knew the establishment would not be supportive. He knew the work could cost Aspect his career. He was essentially saying, "This is important work, and it needs to be done, but make sure they cannot fire you for doing it." Aspect did not yet have a permanent position, but he went ahead anyway. Aspect conducted 3 experiments, published in 1981 and 1982. Each one was more sophisticated than the last. In the first experiment, published in 1981, Aspect and his colleagues used calcium atoms excited by a 2-photon process to produce pairs of entangled photons. They measured the polarization correlations using single-channel polarizers. The result confirmed the violation of Bell's inequality with high statistical significance. In the second experiment, also published in 1981, Aspect used 2-channel polarizers, which allowed both possible polarization outcomes to be measured simultaneously. This improved the statistical power of the experiment and gave results that matched the quantum mechanical predictions with remarkable precision. But the third experiment, published in Physical Review Letters in 1982, was the one that changed history. This was the experiment that addressed the locality loophole. In this experiment, Aspect used acousto-optical switches that could change the direction in which each photon was analyzed. These switches operated very fast. By switching every 10 nanoseconds, the 2 detectors were separated by about 12 meters. Light would take about 40 nanoseconds to travel from one detector to the other, but the switches changed every 10 nanoseconds. This meant that the polarizer setting was changed several times during the time it would take a light signal to travel between the detectors. There was no way for information about the setting at one detector to reach the other detector before the measurement was complete. The locality loophole was closed. The results were devastating for any local hidden variable theory. Bell's inequality was violated with high statistical significance. The measured value of S was approximately 2.697, plus or minus 0.015. The classical limit was 2. The quantum mechanical prediction was approximately 2.7. Aspect's result matched the quantum prediction perfectly and exceeded the classical limit by a massive margin. Let me spell out what this means. In 1982, Alain Aspect proved beyond any reasonable doubt that the correlations between entangled particles cannot be explained by any local hidden variable theory. There are no hidden variables that determine the outcomes in advance. There is no signal traveling between the particles telling them what to do. The correlations are real. They are instantaneous. They exceed the bounds that any local realistic theory can produce. The universe is not locally real. Einstein was wrong. And I want you to understand the full weight of that conclusion. When I say Einstein was wrong, I do not mean he made a small mistake. I do not mean he got a detail wrong. I mean that his fundamental vision of reality, the vision of a universe where things have definite properties, where influences travel at or below the speed of light, where the moon is there whether or not you look at it, that vision was experimentally falsified. The universe does not work that way. The universe is either non-local, meaning instantaneous correlations across any distance are real, or it is not real, meaning things do not have definite properties until they are measured, or both, and the experiment proved it. Not in theory, not in philosophy, in a laboratory, with photons, with data, with numbers. This was, by any reasonable measure, one of the most important experimental results in the history of human civilization. It should have been treated as such. It should have triggered an immediate, worldwide rethinking of everything we thought we knew about the nature of reality. It should have been on the cover of every newspaper, every magazine, every scientific journal. It should have been the talk of every physics department, every philosophy department, every dinner table. Here is what actually happened. The paper was published in Physical Review Letters, one of the most prestigious physics journals in the world. Within the small community of physicists working on the foundations of quantum mechanics, probably fewer than 100 people at the time, the result was recognized as a milestone. Some physicists were genuinely excited, others were disturbed. But in the broader physics community, among the thousands of physicists working on particle physics, condensed matter physics, astrophysics, nuclear physics, applied physics, the result was greeted with something between indifference and a shrug. Yes, quantum mechanics was confirmed. Again. What else is new? Let us get back to real work. There were no press conferences. There was no media sensation. There was no paradigm shift. There was no revolution. The experiment that proved the universe is not locally real was filed away and largely forgotten by the mainstream of physics. Why? This is the question that lies at the heart of this video, and the answer, I believe, is multifaceted and deeply revealing about how science actually works, as opposed to how we like to think it works. The first reason is the one we have already discussed, the shut up and calculate culture. The prevailing attitude in physics for decades had been that the foundations of quantum mechanics were not a legitimate area of research. Questioning the foundations was seen as philosophy, not physics. Real physicists calculated. They predicted. They built things. They did not sit around asking what the wave function really means. This attitude had hardened during the Cold War, when physics funding was tied to military applications, and it persisted well into the 1980s and beyond. The message was clear. If you want a career, work on something useful. Do not waste your time on Bell tests and entanglement. The second reason is related to the first. The career incentives in physics actively discouraged foundational work. If you worked on quantum foundations, you could not get published in the top journals. You could not get grants. You could not get tenure. You were seen as a marginal figure, a philosophical dilettante, not a serious physicist. The examples were numerous and stark. John Bell himself did his foundational work as a side project while his real job was designing accelerators at CERN. John Clauser was marginalized after his groundbreaking experiment. David Bohm, a brilliant physicist who had proposed an alternative to the Copenhagen interpretation, was essentially blacklisted, first politically during the McCarthy era, and then scientifically by the physics establishment. And Alain Aspect was asked by Bell whether he had tenure before undertaking his experiments. The institutional message was unmistakable. This work is dangerous for your career. The third reason is more subtle but perhaps more important. The implications of entanglement were threatening. If you take the results seriously, if you really confront what they mean, you are forced to abandon either locality or realism. And these are not minor concepts. Locality is the basis of special relativity. Realism is the basis of, well, everything. The idea that objects have definite properties, that the world is out there doing its thing whether or not we are watching, this is not just a physics principle. It is the foundation of common sense. It is the foundation of how we navigate the world every single day. If realism fails, then the world is not what it seems. Properties do not exist until they are measured. The moon may not be there when nobody is looking. This is deeply, fundamentally unsettling. And if locality fails, then things that are far apart can influence each other instantaneously. The universe is interconnected in ways that defy our understanding of space and time. This is equally unsettling, and most physicists, like most people, prefer not to be unsettled. They prefer a comfortable universe that behaves itself. The fourth reason is that the implications were considered dangerous in a different sense. In the 1970s and 80s, the foundations of quantum mechanics had become associated with counterculture, with New Age mysticism, with people who wanted to use quantum mechanics to justify all sorts of unscientific beliefs. This association was not entirely unfair. There were indeed people who used the weirdness of quantum mechanics to promote pseudoscience, but the association had a poisonous effect on legitimate scientific inquiry. Serious physicists who wanted to study the foundations of quantum mechanics were tarred with the same brush as the mystics and the charlatans. And so they stayed away. Better to be seen as a serious physicist working on particle physics than to be confused with someone peddling quantum crystal healing. Let me tell you about a remarkable group of people who kept the flame of quantum foundations alive during this dark period. In the 1970s, a group of physicists and physics enthusiasts in Berkeley, California, formed an informal discussion group called the Fundamental Physics Group. The name was deliberately misspelled, a nod to the counterculture. The members of this group were young, creative, unconventional, and deeply interested in the foundational questions of quantum mechanics that the mainstream had abandoned. They discussed entanglement. They discussed Bell's theorem. They discussed the implications for our understanding of reality. They also, it must be said, explored some ideas that were on the fringes of science, ideas about consciousness, about paranormal phenomena, about the role of the observer in quantum mechanics. Some of these ideas were legitimate. Others were speculative to the point of being pseudoscientific. But the point is that these people kept the conversation alive. They kept asking the questions that the mainstream refused to ask. The historian David Kaiser has documented this story in his fascinating book, How the Hippies Saved Physics. And Kaiser argues, convincingly in my view, that the Fundamental Physics Group made genuine and important contributions to physics. Their discussions about entanglement and the no-cloning theorem, the theorem that it is impossible to make a perfect copy of an unknown quantum state, directly influenced the development of quantum information science. The very technologies that are now worth billions of dollars: quantum computing, quantum cryptography, quantum teleportation, trace their intellectual roots, in part, to the discussions of this counterculture group of physicists in Berkeley in the 1970s. The people the establishment called hippies and cranks were, in fact, laying the groundwork for the next technological revolution. I want to dwell on this for a moment because I think it is profoundly important. The history of science is not a smooth, linear march of progress. It is messy, it is political, it is driven by incentives, by career considerations, by cultural norms, by fashion. Ideas that are correct can be ignored for decades because they are unfashionable. Ideas that are wrong can flourish for decades because they are fashionable. The people who make the most important contributions are not always the ones with the biggest names or the most prestigious positions. Sometimes they are outsiders. Sometimes they are rebels. Sometimes they are hippies. And the story of quantum entanglement is perhaps the starkest example of this in the entire history of science. The most important experiment of the 20th century was performed by a young physicist who had to be warned about his career. The most important theorem of the 20th century was published in an obscure journal by an accelerator designer working in his spare time. The implications were suppressed not by any deliberate conspiracy, but by a cultural consensus that made asking certain questions professionally dangerous. And the work that kept the flame alive was done by a group of countercultural outsiders who were ridiculed by the establishment. The universe does not care about our career incentives. It does not care about our cultural norms. It does not care about our comfort. It is what it is, and what it is, as Aspect proved in 1982, is entangled. Now I want to change gears. We have talked about the history. We have talked about the experiment. We have talked about the suppression. Now I want to go deep into the physics itself. I want to explain what quantum entanglement actually is at a level that goes beyond the usual popularizations. I want you to truly understand it, not just the headlines, not just the analogies, the real thing. Let me start by telling you what entanglement is not, because there are many misconceptions, and they are important to clear up. Entanglement is not faster-than-light communication. I know this is what many people believe. I know this is what many popular science articles imply. But it is wrong. You cannot use entanglement to send a message from New York to Tokyo faster than light. The no communication theorem, a rigorous mathematical result, proves this. The reason is subtle but important. When you measure an entangled particle, the result you get is random. You have no control over what the result will be. If you measure the polarization of your photon in New York, you get either vertical or horizontal, and it is completely random, 50-50. There is no way for you to encode a message in a random result. The person in Tokyo sees the same situation on their end. Random results, 50-50. It is only when the two people get together later and compare their results, using a classical communication channel that is limited by the speed of light, that they discover the correlations. They see that every time one measured vertical, the other measured horizontal, and vice versa. The correlations are perfect and instantaneous, but the correlations can only be seen by comparing results, and that comparison requires classical communication, which is limited by the speed of light. So no information is transmitted faster than light. Entanglement does not violate special relativity. Entanglement is not one particle sending a signal to the other. There is no beam of anything, no pulse of energy, no quantum telegram traveling between the particles. The correlation is not caused by communication between the particles. It is a feature of the shared quantum state of the system. The two particles are described by a single joint wave function, not by two separate wave functions. When you measure one particle, you collapse the joint wave function, and this instantaneously affects the probabilities for the other particle, but no signal travels. Entanglement is not magic. It is not mystical. It is not supernatural. It is physics. Strange physics. Counterintuitive physics. Physics that violates our deepest intuitions about how reality works. But physics nonetheless. It is described by precise mathematical equations. It makes testable predictions. And those predictions have been confirmed in thousands of experiments. Now, let me tell you what entanglement is. Start with a simple example. An electron has a property called spin. Spin is a quantum mechanical property with no perfect classical analog, but you can think of it very roughly as the electron spinning like a top, either clockwise or counterclockwise. In quantum mechanics, if you measure the spin of an electron along a particular axis, you get one of two results: spin up or spin down. Before measurement, the electron is in a superposition of spin up and spin down. It does not have a definite spin. Both possibilities exist simultaneously, with certain probabilities. Now, imagine you create two electrons in a way that ensures their total spin is zero. This means their spins must be opposite. If one is spin up, the other must be spin down, and vice versa. This is a conservation law. The total spin was zero before, and it must remain zero after. In quantum mechanics, the two electrons are now described by a single joint wave function. This wave function says the system is in a superposition of two states. State 1, electron A is spin up and electron B is spin down. State 2, electron A is spin down and electron B is spin up. The system is in both states simultaneously. Neither electron has a definite spin. Both are in superposition. But the superposition is not independent. The two electrons are correlated. They are entangled. Now you separate the electrons. Send one to New York, the other to Tokyo. They are 1,000,000 kilometers apart. Their joint wave function is still a single entangled state. Neither electron has acquired a definite spin just because they are far apart. They are still in superposition, still entangled. Now you measure the spin of the electron in New York along, say, the vertical axis. Two possible results, spin up or spin down. You get one of them randomly. Let us say you get spin up. At that instant, the joint wave function collapses. The superposition vanishes. Now the state of the system is definite. Electron A is spin up, electron B is spin down, and this means the electron in Tokyo is now spin down instantaneously, without any signal, without any delay, without any physical interaction. You might say, so what? Maybe both electrons always had definite spins, and measuring one just reveals what the other one is. Maybe it is like a pair of gloves. You put one glove in a box and send it to New York, the other to Tokyo. When you open the box in New York and see a left glove, you instantly know the Tokyo box contains a right glove. Nothing spooky there. The gloves always had definite handedness. No signal was sent. No action at a distance. Just pre-existing correlation. This is exactly what Einstein argued. This is the local hidden variable explanation. The spins were determined when the electrons were created. Each electron had a definite spin all along. Measuring one just reveals the pre-existing information about the other. Nothing non-local about it. And here is where Bell's inequality comes in. Bell showed that this innocent, common-sense explanation, the explanation that says the particles had definite properties all along, makes specific, testable predictions about the correlations between measurements. Specifically, if you measure the spins of the two electrons along different axes, not always the same axis, but sometimes this axis and sometimes that axis, then the correlations between the results are constrained. In any local hidden variable theory, the correlations cannot be too strong. There is a mathematical limit. Bell's inequality. but quantum mechanics predicts that the correlations can be stronger. If you choose the right measurement angles, quantum mechanics predicts correlations that exceed Bell's inequality, and this is exactly what Orsay and Aspect measured. They found correlations that exceeded Bell's inequality. The innocent, common sense, local, realistic explanation does not work. The particles did not have definite spins all along. The correlations are not just pre-existing information being revealed. Something deeper, something stranger is going on. Let me walk through the Bell inequality a bit more carefully, because I want you to really feel the bite of it. Imagine the two electrons are entangled as described, and you can measure each electron's spin along any axis you choose. Let us say you have three possible axes, which we will call A, B, and C. For each measurement, you get either +1, spin up along that axis, or -1, spin down along that axis. Now, in a local hidden variable theory, each electron has a predetermined outcome for every possible measurement axis. Before the measurement, electron 1 already knows what it will give if measured along A, along B, and along C. It has predetermined values for all three. We just do not know what they are. Similarly for electron 2. Given the entanglement, the predetermined values for the two electrons must be opposite. If electron 1 would give +1 along axis A, electron 2 must give -1 along axis A, and vice versa for every axis. Now, let us count the possible predetermined states. Each electron has a definite outcome for each of three axes. For electron 1, there are 8 possible combinations, plus, 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 minus, plus, minus, plus, and so on. For each of these, electron 2 has the opposite values. Let me list them. Electron 1, A+, B+, C+. Electron 2, A-, B-, C-. Electron 1, A+, B+, C-. Electron 2, A-, B-, C+. Electron 1, A+, B-, C+. Electron 2, A-, B+, C-, and so on. 8 possibilities in total. Now, for each measurement, the experimenter in New York randomly chooses to measure along A, B, or C. The experimenter in Tokyo independently and randomly chooses to measure along A, B, or C. They record their results and later compare. What Bell showed is that the correlations between the results, averaged over many measurements, must satisfy a certain inequality in any local hidden variable theory. And for specific choices of measurement angles, quantum mechanics predicts that this inequality will be violated. The quantum correlations are stronger than any local hidden variable theory can produce. The specific difference is not huge in absolute terms. The classical limit might be a correlation coefficient of 2, and quantum mechanics might predict 2.828. But it is a clean, sharp, unmistakable difference. And it has been confirmed in experiment after experiment after experiment. Now, I want to explain something that is often misunderstood. The violation of Bell's inequality does not mean that signals travel faster than light. It does not mean that measuring one particle sends a message to the other. What it means is more subtle and, in a way, more profound. The violation of Bell's inequality means that the correlations between the particles cannot be explained by any combination of pre-existing properties and local interactions. The particles did not have definite values all along, and there is no local mechanism, no signal traveling between them, that creates the correlations. The correlations are a fundamental feature of the quantum state itself. They emerge from the fact that the two particles are described by a single, entangled wave function. They are not two separate things with a hidden connection. They are one thing, masquerading as two. This is what the universe is not locally real means. It means that at least one of our two cherished assumptions, locality, or realism must be wrong. And the experiments show that the combination of locality and realism is wrong. The universe is not both local and real. Something has to give. Different interpretations of quantum mechanics make different choices about what to give up. The Copenhagen interpretation gives up realism. It says particles do not have definite properties until measured. The wave function is a tool for calculating probabilities, not a description of reality. There is no reality to speak of at the quantum level, only measurement outcomes. The many worlds interpretation gives up the uniqueness of measurement outcomes. It says the wave function never collapses. Instead, every possible measurement outcome occurs, each in its own branch of reality. When you measure an entangled particle and get spin up, there is another branch of the universe where you got spin down. Both branches are equally real. The correlations between entangled particles are maintained across branches. Bohmian mechanics, also called pilot wave theory, proposed by David Bohm in 1952, gives up locality but preserves realism. In Bohmian mechanics, particles have definite positions at all times, but they are guided by a wave, the pilot wave, that is non-local. The pilot wave can transmit influences instantaneously across any distance. This preserves realism. Particles have definite properties but violates locality. The cubism interpretation, developed by Christopher Fuchs and others, gives up the objectivity of the wave function. It says the wave function is not a description of reality. It is a description of an agent's beliefs. Quantum mechanics is about how an agent should update their beliefs based on new information. There is no objective wave function. There is no objective collapse. There is just an agent making bets about the outcomes of experiments. There are many other interpretations: relational quantum mechanics, consistent histories, transactional interpretation, objective collapse theories. Each one tells a different story about what quantum mechanics means. Each one gives the same experimental predictions, and no one knows which one, if any, is correct. This is one of the most remarkable facts in all of science. The most successful theory in the history of physics, the theory that predicts experimental results to 12 decimal places of accuracy, the theory that underlies all of modern technology. We do not know what it means. We can use it with extraordinary precision, but we do not understand it. And the physicists who claim to understand it are, in my view, the ones who have not thought about it hard enough. Let me take this deeper. I want to talk about decoherence because decoherence is the key to understanding why we do not see quantum weirdness in our everyday lives, and why entanglement is so fragile. You might ask, if particles can be in superposition, if they can be in two states at once, why don't we see this in everyday life? Why is the moon always there when we look at it? Why is the cat always either dead or alive, never both? The answer is decoherence. Decoherence is the process by which a quantum system loses its quantum properties through interaction with its environment. When a quantum system is isolated, it can maintain superposition and entanglement. But the moment it interacts with a larger system, with air molecules, with photons of light, with the walls of a container, with anything at all, the quantum system becomes entangled with its environment. And this entanglement with the environment effectively destroys the original superposition. Here is how it works. Consider Schrödinger's cat. The cat is supposed to be in a superposition of dead and alive. But the cat is not isolated. It is inside a box surrounded by air. Air molecules are bouncing off the cat's fur, off its whiskers, off the vial of poison. Each of these interactions creates entanglement between the cat and the air molecules. Within a tiny fraction of a second, the cat is entangled not just with the radioactive atom, but with billions and billions of air molecules. And when a quantum system is entangled with billions of environmental particles, the superposition becomes effectively invisible. It does not disappear. The math says it is still there, but it becomes undetectable. The cat appears to be either dead or alive, not both. The superposition is hidden in the correlations with the environment, distributed across billions of particles, impossible to detect with any practical experiment. This is why the quantum world seems so different from the everyday world. It is not that the laws of physics are different for big things and small things. The same quantum mechanics applies to everything. But big things interact with their environment constantly, and this interaction causes decoherence, which makes quantum effects invisible. Small things, like individual electrons and photons, can be isolated from their environment, and so they can exhibit quantum behavior. The line between quantum and classical is not a fundamental divide. It is a practical divide, determined by how well you can isolate a system from its environment. This also explains why entanglement is so fragile. Two entangled particles must be isolated from their environment to maintain their entanglement. The moment one of them interacts with something else, it becomes entangled with that something else, and the original entanglement is diluted or destroyed. This is why quantum computers are so hard to build. Qubits, the quantum bits that quantum computers use, must be kept in a state of near-perfect isolation. Any interaction with the environment causes decoherence, which causes errors in the computation. The engineering challenge of quantum computing is, in large part, the challenge of keeping qubits isolated and entangled for long enough to perform useful calculations. Now, I want to address something that I know many of you are thinking about: the relationship between entanglement and the observer. The idea that consciousness plays a role in quantum mechanics. This is one of the most widespread misconceptions about quantum physics, and I want to address it honestly and carefully. In the Copenhagen interpretation, the measurement problem says that the wave function collapses when a measurement is made. But what constitutes a measurement? Does the measuring device need to be conscious? Does a human observer need to be present? Some early interpretations of quantum mechanics suggested that consciousness might play a special role. Eugene Wigner, a Nobel Prize-winning physicist, proposed a thought experiment called Wigner's Friend, which seemed to imply that consciousness was needed to collapse the wave function. And some people have taken this idea and run with it, arguing that consciousness creates reality, that the observer literally brings the world into existence, that your thoughts can shape the physical world. I need to be very clear about this. This is not what mainstream physics says. The measurement problem is real. It is unsolved. But the idea that consciousness is required for wave function collapse is just one interpretation, and it is not the dominant one. In the decoherence framework, any interaction with a large enough system, conscious or not, causes effective collapse. A camera triggers collapse. A Geiger counter-triggers collapse. A rock triggers collapse. There is nothing special about conscious observers. The universe does not care whether you are watching. It cares whether you are interacting. That said, I do not want to dismiss the deeper question entirely. The measurement problem is unsolved. And some serious physicists, including Roger Penrose and Stuart Hameroff, have proposed theories that link consciousness to quantum mechanics. The Penrose-Hameroff OR theory, for example, suggests that quantum processes in microtubules within neurons might give rise to consciousness, and that consciousness might involve quantum state reductions. This is a legitimate scientific hypothesis, though it is controversial and far from proven. The point is that the relationship between consciousness and quantum mechanics is an open question, not a settled one. And honest science requires us to say that we do not know, rather than claiming certainty in either direction. What I will say is this. Do not let anyone tell you that quantum mechanics proves you can manifest things with your thoughts. Do not let anyone tell you that quantum mechanics proves the power of positive thinking. Do not let anyone sell you quantum crystal healing or quantum meditation or quantum anything that is not actually quantum mechanics. The universe is strange enough without adding pseudoscience to it, and the real implications of entanglement, the actual, demonstrated, Nobel Prize-winning implications, are far more fascinating and far more challenging than any New Age fantasy. All right, let us keep moving forward. Because the story of entanglement did not end in 1982. Far from it. After Aspect's experiments, the study of quantum foundations slowly, gradually, painfully slowly, began to gain some legitimacy. Not because the establishment suddenly changed its mind, but because a new generation of physicists realized that entanglement was not just a philosophical curiosity. It was a resource, a tool, a technology. In the 1980s and 90s, a series of theoretical breakthroughs showed that entanglement could be used to do things that were previously thought impossible. In 1984, Charles Bennett and Gilles Brassard proposed the BB-84 protocol for quantum key distribution, a method of using quantum mechanics to create encryption keys that are provably secure. Any attempt to eavesdrop on a quantum communication channel changes the quantum states being transmitted, alerting the communicating parties to the eavesdropper's presence. This was the birth of quantum cryptography. In 1993, Bennett, Brassard, Crépeau, Josa, Peres, and Wouters proposed quantum teleportation, a method of using entanglement and classical communication to transmit the quantum state of a particle from one location to another. The original particle's state is destroyed in the process, and an identical state is created at the distant location. This is not the teleportation of matter. No atoms move from one place to another, but the information contained in the quantum state is transferred perfectly, instantaneously, to a distant location. In 1985, David Deutsch proposed the concept of a universal quantum computer, a computing device that uses quantum mechanical phenomena, including superposition and entanglement, to perform calculations that no classical computer could perform efficiently. In 1994, Peter Shor discovered a quantum algorithm that could factor large numbers exponentially faster than any known classical algorithm. This was a bombshell because the security of virtually all modern cryptography, including the encryption that protects your bank account, your email, your medical records, is based on the assumption that factoring large numbers is computationally infeasible. A sufficiently powerful quantum computer running Shor's algorithm could break almost all currently used encryption. In 1996, Love Grover discovered a quantum algorithm for searching unsorted databases that was quadratically faster than any classical algorithm. These theoretical results demonstrated that quantum mechanics was not just a curiosity. It was a computational resource of staggering power. And all of these technologies, quantum computing, quantum cryptography, quantum teleportation, all of them depend on entanglement. Entanglement is the fuel that powers the quantum revolution. Without entanglement, there is no quantum computer. Without entanglement, there is no quantum internet. Without entanglement, there is no unbreakable encryption. The phenomenon that Einstein called spooky, that the physics establishment ignored for decades, that Aspect proved in a French laboratory in 1982, that phenomenon is now the foundation of a technological revolution worth trillions of dollars. The irony is almost too perfect. The discovery that was buried is now building the future. But the experimental story was not over either. Remember those loopholes I mentioned? Aspect closed the locality loophole in 1982, but the detection loophole remained open. And there was another loophole, the freedom of choice loophole, the possibility that the random number generators used to set the measurement angles were somehow predetermined, it correlated with the hidden variables. To truly, definitively rule out all local hidden variable theories, all loopholes had to be closed simultaneously in a single experiment. This was achieved in 2015, in a landmark experiment at the Delft University of Technology in the Netherlands, led by Ronald Hansen. The Delft experiment used nitrogen vacancy centers in diamonds. These are tiny defects in the crystal structure of diamond that can trap single electrons. The electron's spins can be entangled across large distances using a clever technique called entanglement swapping. In the Delft experiment, two entangled electrons were separated by 1.3 kilometers on the university campus. The measurement settings were chosen using quantum random number generators, ensuring true randomness. And crucially, the experiment was designed so that both the locality loophole and the detection loophole were closed simultaneously. The result, Bell's inequality, was violated. The measured p-value was 0.039, meaning there was less than a 4% probability that the result could be explained by a local hidden variable theory. Subsequent repetitions of the experiment, with more data, reduced this probability further. The Delft experiment was the first truly loophole-free Bell test in history. For the first time, there was no escape. No way to explain the results using local hidden variables. No loophole to hide in. The universe is not locally real, period. But the scientific community, being the thorough and cautious body that it is, did not stop there. In the same year, 2015, two more loophole-free Bell tests were performed. One at the National Institute of Standards and Technology in Boulder, Colorado, using entangled photons. Another at the University of Vienna by Anton Zeilinger's group. Both confirmed the violation of Bell's inequality with all loopholes closed. And then, in 2018, Zeilinger's group pushed the boundaries even further. They performed what they called a cosmic Bell test. In this experiment, instead of using quantum random number generators to choose the measurement settings, they used the color of light arriving from distant stars and quasars. The light from these celestial objects was emitted hundreds of years ago, and in some cases billions of years ago. By using this starlight to choose the measurement settings, the experimenters ensured that the settings could not have been predetermined by any local mechanism going back hundreds or even billions of years. This closed the freedom of choice loophole back to the very earliest moments of the universe, or very close to it. The only way to maintain a local hidden variable theory in the face of this experiment would be to hypothesize a conspiracy, a cosmic conspiracy, in which the hidden variables were set at the beginning of the universe, 14 billion years ago, in a way that would produce results mimicking quantum mechanics in an experiment in Vienna in 2018. This is technically not impossible, but it is, by any reasonable standard, absurd. The verdict was final. After 50 years of testing, after closing every conceivable loophole, the answer is clear. Bell's inequality is violated. The universe is not locally real. Quantum mechanics is correct. Einstein was wrong. And this brings us to 2022 and the moment when the physics establishment finally, belatedly, acknowledged what had been proven decades earlier. On October 4th, 2022, the Royal Swedish Academy of Sciences announced the Nobel Prize in Physics. It was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Alain Aspect was 75 years old when he received the call. John Clauser was 79. They had waited their entire careers for this recognition. Clauser had performed his first Bell test in 1972, 50 years before the Nobel Prize. Aspect had performed his definitive experiment in 1982, 40 years before. Half a century. That is how long it took the scientific establishment to acknowledge the importance of their work. Half a century of marginalization. Half a century of shut up and calculate. Half a century of being told that their work was not real physics. And there is a painful absence in this story. John Bell, the man who made it all possible. The man who proved the most profound theorem in the history of physics. The man who turned philosophy into experiment. John Bell died on October 1st, 1990, of a cerebral hemorrhage. He was 62 years old. He never received the Nobel Prize. Many physicists believe he would have won it if he had lived. The Nobel Prize is not awarded posthumously. And so the man who arguably deserved it more than anyone was denied it by timing and by the decades of delay in recognizing the importance of his work. I want to pause here and let that sink in. John Bell died without the recognition he deserved, because the physics community spent decades ignoring the implications of his work, because shut up and calculate was more important than understanding reality, because asking the wrong questions in the culture of physics was worse than asking no questions at all. There is something tragic about this, and there is something important about it. The lesson is that science does not always reward the people who make the biggest contributions. Sometimes the people who matter most are the ones who are ignored the longest. Sometimes the most important discoveries are the ones that take the longest to be recognized. And sometimes the price of asking the right question is that you do not live long enough to see the answer. The third Nobel laureate, Anton Zeilinger, deserves his own attention in this story. Zeilinger, an Austrian physicist, was born in 1945. He is known as the Pope of quantum physics for his showmanship and his ability to communicate the excitement of quantum mechanics to the public. But his scientific contributions are no less important than his public persona. Zeilinger's group at the University of Vienna performed some of the most spectacular demonstrations of quantum entanglement in history. In 1997, Zeilinger's team, along with several collaborators, achieved the first experimental demonstration of quantum teleportation. They teleported the quantum state of a photon from one location to another using entanglement and classical communication. This was the first time that the theoretical protocol proposed by Bennett and collaborators in 1993 was actually carried out in a laboratory. It was a landmark moment in the history of physics. Zeilinger's group went on to demonstrate entanglement over increasingly large distances. They demonstrated entanglement across the Danube River in Vienna. They demonstrated entanglement between the Canary Islands, a distance of 143 kilometers. They demonstrated entanglement using satellites, sending entangled photons from space to ground stations thousands of kilometers apart. Each of these experiments pushed the boundaries of what was thought possible, and demonstrated that entanglement is a robust, scalable phenomenon that can be exploited for practical applications. Zeilinger also made important contributions to the concept of entanglement swapping, a technique for entangling particles that have never interacted directly by performing measurements on other particles that are entangled with them. This technique is essential for building quantum networks, where entanglement must be distributed across many nodes. I want you to see the arc of this story. In 1935, entanglement was a thought experiment, a philosophical objection raised by Einstein against quantum mechanics. In 1964, Bell showed it could be tested. In 1972, Clauser tested it and was marginalized. In 1982, Aspect proved it and was ignored. In the 1990s, it became a technology. In the 2000s, it became a billion-dollar industry. In 2022, it won the Nobel Prize. The trajectory is from ridicule to recognition, from suppression to celebration, from a buried experiment to the foundation of a new era of technology. And this brings me to where we are now, because the quantum revolution is not a future event. It is happening right now, and entanglement is at the center of it. Let me tell you about what is happening in quantum computing. Quantum computers use qubits instead of classical bits. A classical bit can be either 0 or 1. A qubit can be in a superposition of 0 and 1, effectively being both at the same time. And when qubits are entangled with each other, the computational possibilities explode. An entangled system of n qubits can represent 2 to the power of n states simultaneously. 50 entangled qubits can represent more than a quadrillion states at once. This massive parallelism is what gives quantum computers their power. Companies and governments around the world are investing billions of dollars in quantum computing. IBM has built quantum processors with over 1,000 qubits. Google claimed quantum supremacy in 2019 with its Sycamore processor, which performed a specific calculation in 200 seconds that would have taken the most powerful classical supercomputer an estimated 10,000 years. China has built quantum computers that have demonstrated quantum advantage in specific tasks. Startups like IonQ, Rigetti Computing, and others are building their own quantum systems.